Hello dear students, all of you welcome to Vidyan classes. It is the 6th lecture on function in the chapter relations and functions. Today we will discuss some important theorems on composition of functions. First theorem, if f is a function from x to y, g is a function from y to z and h is a function from z to v, then composition of H and G is the same as composition of H and F. That is, composition is associative. It is the properties of associative. Proof. It is x, it is y, it is z, and it is v. F is a function from x to y. G is a function from y to z. And h is the function from z to v. X is an element in capital X. Small y is an element in capital Y, and small z is an element in capital Z, and small v is an element in capital V. F operates on x gives y, g operates on y gives z, h operates on z gives v. Clear? These are given. Since f is a function from x to y, and g is a function from y to z, it is defined by g is the function. G is the function defined from x to z. Again we have g is a function from y to z and h is a function from z to v. So g is a function from y to z, h is the function from z to v. So h is the function from y to v. F is the function from x to z and h is the function from y to v. Now we have g is the function such that x to z and h is the function such that z to v. Implies this. G is the function from x to z and h is the function from z to v. So composition of h and g so that it is x to z, it is z to v. So composition h and g so that x to z. Clear? G is the function from x to z and h is the function from z to v. So composition h and g from x to z. Again we have f is a function from x to y. F so that x to y. And hug, that is the composition of g and h so that y to x to it is x to z, it is x to v. G is a function from x to z and h is the function from z to v. So composition of h and g x to v. Here f is a function from x to y, f is a function from x to y, hug is the function y to v. By the composition, which implies the composition of this hug, composition to f such that x to y, y to v, that is the s to v. It is equation 1. It is 2. From equation 1 and equation 2, we have both functions, this function and this function have the same domain and codomain. From equation 1 and 2, we have done H composition of composition of H and Guf is equal to dom of composition which is equal to x, capital X. Both have the same domain. Both functions are exist from x to v. From equation 1 and 2, we have dom H composition of Guf is same as dom of composition of f which is equal to x. It is equation 3. We have to show this function is same as this function. Two functions are equal if they have same domain and same range for the given domain. The domain set is x. For x belongs to capital X. H composition of x which is same as Guf x is written as g f x. Guf it is g, it is f. Guf x is written as g f x, that is H Guf x. G f x. It is G f. Guf x is same as G f x, which is same as Guf is same as G f x. Clear? Guf x is written as Guf x is written as G f x. Guf x is written as G f x. It is G H, it is F H f x. Again, Guf x is equal to G f x. F x. G f x. Guf x is equal to G f x. The left bracket is 1, 2, 3, right bracket is 1, 2, 3. Okay. It is GOP X. Again, how composition F X. It is F, it is G, it is F. GOP X equal to GFX. GOP X is equal to written as GFX. That means GOP how FX. GFX. GFX. It is G, it is F, GFX. Which is same as GFX. Clear? It is G, it is F, so it is G Fx. GFX. Now it is X, it is F, it is G, H, G Fx. Clear? It is G, it is F, it is X. GOP X equal to GFX. So H GFX. Clear? Clear? It is G4, it is G5. From equation clear? GOP X. It is G, it is F, it is X, that is GFX. From equation 3 and 4 and 5, equation 4 and 5. We have is equal to this right hand side of equation 4 and 5 are same, so the left hand sides are equal, which is equal to half x implies range H composition GOP is the same as range of composition F. It is 6. Clear? Range of this function is same as range of this plane. Domain of this function is same as domain of this function. Equation 3 and equation 6 implies this. Since the composite function have same domain and same range, implies this. Equation 3 and equation 6 implies this. H composition GOP is the same as hog composition F. Equation 3 and equation 6 implies this. The composite functions have same domain. This composite function and this composite function have same domain and same range. So the two functions are equal. That is, it satisfies the properties of associative. Composition is associative. composition is associative, hence proved. Clear? Once again, f is a function from s to y, g is a function from y to z, h is the function from z to v. Now we have, since f is the function from s to y, g is the function from y to z, it is defined by g is the function from s to z. H is the function from z to v. Since g is the function from x to z and h is the function z to v, by the composition, h composition g is a function from x to v. Again we have f is the function from x to y and hog is the function from y to v. By the composition f is x to y, y to v, that is x to b. These two functions have same domain and same codomain. From equation 1 and 2 we have term of this is same as term of this, that is x. The two functions have the same domain. We have to show if they have same range, then the two functions will be equal. For x belongs to capital X, h composition g of x, which is same as g of x is written as g of x. It is g, it is f, g of x. Again g of x is written as g f x. Clear? G of x is written as g f x. The left bracket 1, 2, 3, right bracket 1, 2, 3. Again hog composition f x. It is g, it is f. So g f x, g f x. Now h composition to g, that is g and f, that is h g f x. Clear? Clear? Now equation 4 and 5 have same value in the right hand side. So the left value is equal to left value of 4 and 5, since they have same value in the right hand side. From equation 4 and 5 we have this is same as this. The left value is this and the right value is this. Composition of this and the composition of this are equal, since the right hand sides are equal. That means range of the composite function is same as the range of this composite function. Range of this is same as range of this for the given domain. For x belongs to capital X, range of this function is the range of this function. Now we have these two functions have same domain and the same range, implies the two functions, equation 3 and 6 implies the two functions are equal. Since it is satisfied the definition of associative, that is composition is associative, hence proved. Hence proved. Clear? Clear? Okay. Note down. Second theorem, Elements of Mathematics, page number 18. If f is a function from x to y and g is a function from y to z, then g is onto if both f and g are onto. Proof. F is a function from x to y. G is a function from y to z. x is an element in x, small y belongs to capital Y and small z belongs to capital Z. Gop is the function from x to z. Given f such that x to y is onto f and g both are onto implies by the definition for every y belongs to capital Y, there exists at least an element x belongs to capital X such that fx is equal to y. It is the definition of onto. Since x to y is onto. Also we have g so that y to z is onto. Implies this for every z belongs to capital Z, there exists at least an element y belongs to capital Y so that for every z belongs to capital Z, there exists at least an element y belongs to capital Y so that g of y is equal to z. Equation 2. fx is equal to y, gy is equal to z. To show these are given. To show gop so that x to z is onto. For every z belongs to capital Z, there exists at least an element x, since gop is the function defined from x to z, capital X. For every z belongs to capital Z, there exists at least an element x belongs to capital X, so that gop x. If gop x is equal to z, then gop is onto. Now we have to show gop x is equal to z, which is same as g of fx. By equation 1, fx is equal to y, which is equal to g of y by equation 1. G of y is equal to z by equation 2, which satisfies the definition. For every z belongs to capital Z, there exists at least an element x belongs to capital X, so that of x is equal to z. Therefore, of such that x to z is on 2. Hence, proved. Using the definition of onto, we can prove theorem 2 of first bit. It is the first bit. There are 4 bits in theorem 2. Clear? Note down. Very easy question. Next, theorem 2, second bit. If f such that x to y and g such that y to z, then GOF is 1 1 if f and g are 1 1. Proof. F is a function from x to y and g is a function from y to z. GOF is the function from x to z. To show GOF is 1 1. When? To show GOF is such that x to z is 1 1. When both f and g are 1 1. To show GOF is 1 1 when f and g are 1 1. By the definition, for every x1 x2 belongs to capital X, GOF x1 is equal to GOF x2. That implies the function f such that x to y is said to be 1 1 if for every x1 x2 belongs to domain set fx1 is equal to fx2, that implies x1 equal to x2. GOF fx1 is equal to g fx2, which implies fx1 is equal to fx2. Since g fx1 is equal to g fx2, since g is 1 1. Since g is 1, gx1 equal to gx2, that implies x1 equal to x2 since g is 1 1. Here x1 is fx1, x2 is fx2, which implies x1 is equal to x2. Since f is 1 1. Now we have For every x1 is x2 belongs to capital X, GOF x1 is equal to GOF x2 implies x1 is equal to s2. Therefore, GOF so that x2z is 1 1. Since GOF satisfies the definition of a 1 1 or injective, hence proved. Easy question. Clear? Next, theorem 2, third bit. If f such that x to y and g such that y to z, then GOF is g is onto if GOF is onto. Proof. F such that x to y, g is the function from y to z, x, y, z. F operates on x gives y, g operates on y gives z. GOF is the function defined from x to z. To show g onto, given GOF such that x to z is onto. By definition, for every z belongs to capital Z, there exists x belongs to capital X, there exists at least an element x belongs to capital X so that GOF x is equal to z. It is the definition of onto. For every z belongs to capital Z, there exists at least an element belongs to capital X so that GOF x is equal to z, which is same as g of fx is equal to z, which is same as gy is equal to z. Since f operates on x gives y, since f such that x to y is a function, fx is equal to y for x belongs to capital X. F operates on x gives f is a function from x to y, fx is equal to y for x belongs to capital X and y belongs to capital Y. F operates on x gives y. It is satisfied gy equal to z. G of fx is equal to z, that implies g of y is equal to z. Implies yes. For every z belongs to capital Z, there exists at least an element y belongs to capital Y such that gy is equal to z. Therefore, gy is equal to z implies for every z belongs to z there exists at least an element y belongs to capital Y such that gy is equal to z. It is the definition of onto. Therefore, G such that y to z is G onto. G equal to Z satisfies this condition. For every Z belongs to capital Z, there exists at least an element Y belongs to Y such that Gy is equal to Z. Therefore, G such that Y to Z is G onto. When Guff is onto. Clear? Okay. Note down. Next. Theorem 2, fourth bit. If f such that x to y and g such that y to z, then f is 1 1 if Guff is 1 1. Proof. F is the function from x to y, g is the function from y to z. It is defined by Guff is the function from s to z. Let giving Guff is 1 1. To prove f is 1 1. Let Guff such that s to z is 1 1. To show f is 1 1. Given Guff such that x to z is 1 1 to show f is 1 1. It can be proved. By the method of contradiction. The statement can be proved by the method of contradiction. If possible, to show f is 1 1. If possible, let f is not 1 1. If possible, let f is not 1 1. What is 1 1 function? F such that x to y is 1 1 for every x1 x2 belongs to capital X, x1 not equal to x2, that implies fx1 not equal to fx2, or f such that x to y is 1 1 for every x1 x2 belongs to capital X, fx1 is equal to fx2 that implies x1 is equal to x2. F such that x2 y is 1 1 if this condition satisfied or this condition satisfied. Here we have taken f is not 1 1. Let x1 x2 belongs to f is the function from x to y, capital X. x1 not equal to x2, but fx1 is equal to fx2. Since f is not 1 1, if f is 1 1, x1 not equal to x2 implies fx1 not equal to fx2. Here, since f is not 1 1, x1 not equal to x2, but fx1 is equal to fx2. Clear? Since f is not 1 1. Now, g of fx1, which is same as g of fx1 is taken as fx2. fx2. Now g of fx1 is same as fx2, g of fx2. That implies gf x1 is equal to gf x2. Gf x1 is written as g of fx1. Gf x2 is written as g of fx2. So we can write g of fx1 is equal to this, g of fx2 is equal to this. But x1 not equal to x2, which contradict to the fact that gf is 1 1. Gf is 1 1 means gf x1 is equal to gf x2, that implies x1 equal to x2. Here x1 not equal to x2. Gf x1 is equal to gf x2. Since gf is 1 1, it implies x1 is equal to x2. Clear? But it is given by x1 not equal to x2, which contradicts to the fact that gf is 1 1. Clear? Gf is 1 1 means gf x1 is equal to gf x2, that implies x1 equal to x2. Here we have taken x1 not equal to x2, which contradicts to the fact that gf is 1 1. So our assumption is false. Our assumption is false. What is the assumption? We assumed f is not 1 1. So our assumption is false. That is the given statement is true. Our assumption is false. That is, the given statement is true. What is the given statement? If gf is 1 1, f is 1 1. So gf is 1 1 implies f is 1 1. Hence proved. Clear? Once again, f is a function from x to y, g is a function from y to z. We have to show f is 1 1. If gop is 1 1. Gop is 1 1 implies f is 1 1. The statement can be proved. Gop so that x2 z is 1 1 to show f is 1 1. The statement can be proved by the method of contradiction. That means it can be proved by the method of contradiction. If possible, let f is not 1 1. By the definition of 1 1, for every x1 x2 belongs to capital X1, x1 not equal to x2, that implies fx1 is equal to fx2. Or we can say for every x1 x2 belongs to capital X, fx1 is equal to fx2, that implies x1 is equal to x2. Is the definition of 1 1. Since f is not 1 1, for every x1 x2 belongs to capital X, x1 not equal to x2, but fx1 is equal to fx2. It is the condition that the function will be 1 1. Since f is not 1 1, we consider x1 not equal to x2, but fx1 is equal to fx2. Clear? Now g of fx1 is the same as fx2. G of fx1 is equal to g of fx2, since fx1 is equal to fx2. But this can be written as gop x1, this can be written as gop x2. Gop x1 is equal to gop x2, but x1 not equal to x2. We assumed f is not 1 1. Clear? Which contradicts to the fact that gop is 1 1. So our assumption is false, that is, the given statement is true. What is the given statement? Gop is 1 1 implies f is 1 1. So gop is 1 1 implies f is 1 1. Hence it is proved. Hence it is proved. Clear? Okay. Note down. Next, theorem 3. Let f so that x to y, then the relation f inverse is a function from y to x if f is bijective. Proof. Given f so that x to y is bijective, let f so that x to y is a bijective function. Which implies and implied by f is 1 1 and on 2. Every bijective function is 1 1 and 2. Every bijective function is 1 1 and on 2. F is a bijective function from x to y. To show the relation f inverse so that y to x is a function. We have to show the relation f inverse so that y to x is a function. The relation f inverse is a function from y to x, which implies and implied by. What is the definition of function? F inverse, it is y, it is x. F inverse from y to x is a function. What is the definition of function? What is the definition of function? Domain of f inverse is equal to y. Y z order pair belongs to f inverse. Y t order pair belongs to f inverse. That implies z is equal to t. It is the definition of a function, which implies and implied by first term f inverse is equal to y. Second condition, y z order pair belongs to f inverse and y t order pair belongs to f inverse. That implies z is equal to t. If these two conditions are satisfied, then f inverse is a function from y to x. Proof of first. Domain of f inverse is equal to y. Since f so that x to y is onto implies this. By the definition, for every y belongs to capital Y, every y belongs to capital Y, there exists an element x belongs to capital X, so that fx is equal to y. It is the definition of onto function. Since f so that x to y is onto, for every y belongs to capital Y, there exists an element x belongs to capital X, so that fx equal to y, which implies xy order pair belongs to f. Fx equal to y. F operates on x gives y. F operates on x gives y. Xy order pair belongs to f. Yx order pair belongs to f inverse. Xy order pair belongs to f. That implies yx order pair belongs to f inverse. Clear? Which implies this. It is the domain. It is the y is the domain. Any element of the domain. Y belongs to dom f inverse. Here y is an element. Y is the any element in the domain set, which implies this. Clear? Y belongs to domain of f inverse. Since y belongs to capital Y, since y belongs to capital Y, since y belongs to capital Y, that implies y belongs to dom f inverse. Implies this. Every element of capital Y is the element of this. So y subset or equal to dom f inverse. It is equation 1. Since y belongs to capital Y, it is the definition of a subset. Every element of y is the element of a DOM of F inverse. So y subset or equal to F inverse. It is clear that DOM F inverse, domain of F inverse, subset or equal to y. Domain of F inverse, subset or equal to y. It is the second equation. From equation 1 and equation 2, we get A subset of B subset of A. That means A equal to B. Y subset of this subset of Y. We get from equation 1 and equation 2, we get DOM F inverse is equal to capital Y. So, therefore, first part, DOM of F inverse is equal to Y. Therefore, first part is proved. Clear? From equation 1 and 2, we get DOM of F inverse, this subset of this subset of this, so this equal to this. Second part, clear? Okay. Second part. Yz belongs to F inverse and Yt belongs to F inverse, that implies Z is equal to T. Yz belongs to F inverse and Yt belongs to F inverse. That implies Y operates F inverse, operates on Y gives Z. F inverse of Y is equal to, Yz belongs to this, Zy belongs to F. By the definition of a inverse function, Yz belongs to F inverse, Zy belongs to F, and Yt belongs to F inverse, Ty belongs to F. Now, F operates on Z gives Y, F operates on T gives Y. Now we have Y is equal to this value, Y is equal to this value. Fz is equal to Ft. Here, which implies Z is equal to T. Since F is 1, 1, Fx1 equal to Fx2, x1 equal to x2. It is the definition of a 1, 1. Since F is 1, 1. Yz belongs to F inverse, Yz belongs to F inverse and Yt belongs to F inverse, that implies Z is equal to T. Therefore, second part is proved. Clear? Here first part is proved, here second part is proved. There second part is proved. Since f such that x to y is bijative, hence x2y, hence f such that x2y is divisable. So f such that x2y is divisable. So f such that x2y is divisable implies this f inverse such that y2x is a function. Clear? F such that x to y is divisable implies f inverse y to x is a function. Hence proved. Hence proved. F such that x to y is divisable. Divisable means 1 1 and 1 2. We have to show the relation f inverse such that y to x is a function. F inverse is a function if these two conditions are satisfied. Since f such that x to y is onto, by the definition, for every y belongs to capital Y, there exists an element x belongs to capital X, so that fx is equal to y. Fx is equal to y, that means xy order pair belongs to f. Yx order pair belongs to f inverse. Implies this y is equal to what is y? Is the element of a domain of a f inverse. Y belongs to capital Y. Y belongs to this. Y belongs to capital Y implies this y belongs to term of a f inverse. That implies y subset or equal to term of a f inverse. Clear? It is clear that domain of a f inverse belongs to this set. So domain of a f inverse subset or equal to y. It is clear that term f inverse subset or equal to y. Here y subset or equal to this, and this also subset equal to this. From equation 1 and 2 we get domain of f inverse is equal to y. A subset of b, b subset of a, that is a equal to b. This subset of this subset of this, so this equal to this. Second part, yz belongs to yz order pair belongs to f inverse, yt order pair belongs to f inverse. We have to show z equal to t. Yz order pair belongs to f inverse and yt order pair belongs to f inverse zy. Yz belongs to this, zy belongs to f. Clear? By the definition of a inverse relation or function, yt belongs to f inverse, ty belongs to f. F operates on z gives y, f operates on t gives y. Y is equal to this result, y is equal to this result, fz is equal to ft, which implies z is equal to t, since f is 1 1. The function f is said to be 1 1 for every x1 x2 belongs to a, f x1 equal to f x2, that implies x1 equal to x2. Since f is 1 1, z is equal to t. So the second part is proved. This belongs to this belongs to this, implies z is equal to t. So f such that x2, it is a given part, it is the proof part. F such that x to y is divisible implies f inverse y to x is a function. Hence proved. Most important theorem on elements of mathematics, page number 20. Most important long question. Clear? Clear? Okay. Note down. No doubt. Next, theorem 4. If f such that x to y is bijective, then f inverse composite to f is equal to idx, and f composite to f inverse is equal to idy, where idx and idy are identity functions on x and y respectively. Proof. Let f such that x to y is bijective. To show f inverse composite to f is equal to idx, that means identity function on x, and f composite to f inverse is equal to idy. Since f such that x to y is bijective, implies f inverse is exist. Since by the previous theorem f such that x to y is bijective, f such that x2 is bijective implies f in the relation f inverse such that y2 x is a function. It is proved in the previous theorem. Since f such that x to y is bijective, f inverse is exists. Since in the previous theorem we have proved f such that x to y is bijective, that implies the relation f inverse such that y to x is a function. To show f inverse composite to f is equal to idx, let y is equal to f inverse composite to fx. For every x belongs to capital X. Since f is a function from x to y, this can be written as g of x is written as g f x. So this can be written as f inverse fx. F inverse is treated as g, which implies fx y order pair belongs to f inverse. F inverse operates on fx gives y. This and this are same meaning, which implies y fx order pair belongs to f. xy order pair belongs to f inverse, yx order pair belongs to f. By the definition of an inverse function, fx y order pair belongs to f inverse, interchanging y fx order pair belongs to f, which implies f operates on y, f operates on y is equal to fx. which implies x is equal to y. Since f is bijective, that is f is 1 1 and on 2. F is 1 1. Since f is bijective, that means f is 1 1. Now y is equal to x. What is the value? Y is equal to f inverse composite to fx. F inverse composite to fx is equal to x, which is same as I dx. Since I dx is equal to set of x's order pair, so that for all x belongs to capital X. That means I dx operates on x gives x, or I dx x is equal to x for all x belongs to capital X. Here, since I dx operates on x gives x, implies f inverse composite to f is equal to x is equal to I dx x. That implies f inverse f is equal to I dx. For the given domain, since the functions have same domain and same range, for every x belongs to capital X, the two functions, this and this, have the same range, therefore the two functions are equal. X belongs to capital X, this is same as this, so this is equal to this. Two functions are equal if they have same domain and the same range for the given domain. Here the given domain is capital X, since f is the function from x to y. Implies f inverse composite to f is equal to I dx. The two functions are equal. Similarly, we can prove the second part, that is f composite to f inverse is equal to I dy. Let t is equal to f composite to f inverse y. Let t is equal to this. For every y belongs to capital Y. Since f inverse is a function, is a bijective function, which implies t is equal to f inverse y. Fog can be written f of gx, it is gx. Clear? This can be the same as this, which implies f inverse y t order pair belongs to f. Clear? Which is same as f inverse t F inverse y order pair belongs to F inverse. F inverse is a bijective function, that is 1 1 and 1 2. F inverse t is equal to F inverse y, which implies t is equal to y. Since F inverse, F is a bijective function, F inverse exists, which is also a bijective function. That means 1 1 and 1 2. T is equal to y. What is the value of t? What is t? F composite to F inverse y is equal to y. Y can be written as I dy y. Since I dy y is equal to y, it is the definition of a since I dy y is equal to y for all y belongs to capital Y. For every y belongs to capital Y, the two functions are equal. It is for every y belongs to capital Y, f composite to f inverse y is equal to I dy y. That means the two functions have the same domain and the same range, therefore the functions are equal. F inverse is equal to I dy y. Clear? F composite to F inverse is equal to I dy and F inverse composite to F is equal to I dx. Clear? Therefore, F inverse composite to F is equal to I dx and F composite to F inverse is equal to I dy, where I dx and I dy are two identity functions on x and y respectively. Hence proved. Hence proved. Clear? Clear? Okay. Note down. Next, theorem 4, second part. If f such that x to y and g such that y to z are two invertible, that means bijective functions, then part A, GOP is invertible, that is bijective. Part B, GOP inverse is equal to F inverse composite to G inverse. Proof. It has two parts. Part A. F is a function from x to y. G is a function from y to z. X is any element in capital X. Y is any element in capital Y. Z is any element in capital Z. Since f is invertible, f inverse is the function from y to x. Since g is invertible, G inverse is a function from Z to Y. F is the function from X to Y. G is the function from Y to Z. So GOF is the function from X to Z. Clear? F is a function from X to Y. G is a function from Y to Z. F operates on X gives Y. G operates on Y, it gives Z. Given F such that X to Y and G such that Y to Z are two invertible, that is bijective functions. Clear? F is a function from X to Y is invertible. G is a function which is also invertible. Invertible means bijective. Bijective, every bijective function is 1, 1 and on 2. Since F such that X to Y is invertible, by definition it implies this. Fx is equal to Y implies it by X is equal to F inverse Y. For every X belongs to capital X and Y belongs to capital Y. Since F so that X to Y is invertible, by the definition of inverse function, Fx is equal to Y, that implies it by X equal to F inverse Y. For every X belongs to capital X and Y belongs to capital Y. Clear? It is the definition of inverse function. Again, G so that Y to Z is invertible. That means the inverse is exist. The function is bijective, which satisfies the 1, 1 and on 2 conditions. Again, G so that is invertible. By the definition, it implies this. Gy is equal to Z implies by G inverse of Z is equal to Y. For every Z belongs to, capital Z and Y belongs to capital Y. And Y belongs to capital Y. It is the condition 1, it is the condition 2. To show GOF is the function defined from X to Z, so that capital X to Z is invertible. That means bijective. To show GOF is invertible, which implies it by GOF is surjective and injective. Invertible means bijective. To show Goff is invertible. That means Goff is surjective and injective. Test for surjective. By the definition, for every Goff is the function from x to z. For every z belongs to capital Z, there exists an element x belongs to capital X, so that Goff for every z belongs to capital Z, there exists an element x belongs to capital X, so that Goff x is the same as g of fx. Goff x is written as g of fx, which is same as, what is fx? Equation 1 implies this fx is equal to y. Since f is invertible, gy by equation 1, which is same as gy is equal to z. Gy is equal to z by equation 2. For every z belongs to capital Z, there exists an element x belongs to capital X, so that Goff x is equal to z. It is the definition of surjective. So Goff satisfies the definition of surjective. Therefore, Goff, so that x to z is surjective. Clear? Goff so that x to z is surjective. The first part is proved. That is Goff is surjective. Test for onto. Sorry. Test for injective. Test for injective. By the definition, for every x1, x2 belongs to domain of f, that is x, Goff x1 is equal to Goff x2 implies this. Goff x1 is written as g f x1. Goff is written as g f x. So Goff x1 is written as g f x1. Similarly, g f x2, which implies this f x1 is equal to f x2. Why? Since GG 11 or injective. Since GG 11, Gx1 is equal to Gx2 implies this x1 is equal to x2. Here x1 means fx1, x2 means fx2. GG invertible. So GG 11 and on 2 implies this. X1 is equal to x2, fx2 is equal to fx1, x1 equal to x2. Since f is 11 or injective. Since f is 11. Now we have for every x1, x2 belongs to capital F, capital X, GOF x1 is equal to GOF x2, that implies x1 equal to x2. It is the definition of a 1, 1. Therefore, GOF such that x2z is injective. That is 1, 1. GOF is subjective, GOF is injective. In general, GOF such that x2z is invertible, that is bijective. Bijective means injective and subjective. Here, in general, GOF such that x2z is invertible. So that GOF is invertible. Here, once again, given f and g are invertible, given f such that x2y and g such that y2z are two invertible functions. Since f such that x2y is invertible, implies this fx is equal to y, that implies x is equal to f inverse y. It is the definition of an invertible function. That means the function is invertible, means its inverse is exist. Similarly, g such that y2z is invertible, that means its inverse is exist, which implies this gy is equal to z, implies by g inverse z is equal to y for z belongs to capital Z, for every z belongs to capital Z and y belongs to capital Y. To show GOF such that x2z is invertible. Invertible means bijective. Bijective means it is surjective and injective. GOF is surjective and injective. Test for surjective. For every z belongs to capital Z, there exists an element x belongs to capital X such that GOF x is equal to g of fx. GOF x is the same as g of fx. Fx is equal to y by the equation 1. By equation 1, fx is equal to y. Gy is equal to z by equation 2. By equation 2. For every z belongs to capital Z. For every z belongs to capital Z, GOF x is equal to, for every z belongs to capital Z, there exists an element x belongs to capital X such that GOF x is equal to z. It is the definition of surjective. Therefore, GOF such that x2z is surjective. Test for injective. For every x1, x2 belongs to capital X, GOF x1 is equal to GOF x2, which is same as g of fx1. It is same as g of fx2. GOF x1 equal to g of fx1, GOF x2 is equal to g of fx2. Implies this fx1 is equal to fx2 since g is 1, 1. Since g is invertible, that means 1, 1 and on 2. implies this fx1 equal to fx2. fx1 equal to fx2, that implies x1 is equal to x2 since f is 1 1. Since f is invertible. Therefore, GOF such that x2z is injective. Since GOF satisfies the definition of injective. In general, GOF such that x2z is invertible, that is means its inverse is exist. Imply f is in, which implies GOF inverse z is equal to x. Clear? Hence the statement. Hence A is proved. GOF is invertible. Clear? Okay. Note down. Next, part B. In part B, we have to show GOF inverse is equal to F inverse composite to G inverse. Proof. Part B. F is the function from x to y. G is the function from y to z. GOF is the function from x to z. F operates on x gives y. G operates on y gives z. F inverse is the function from y to z. F G inverse is the function from z to y. F is the function from x to y. F inverse is the function from y to x. Since f and g are invertible. In part A, we have proved GOF is invertible. GOF inverse is the function from z to x. Clear? It is the figure to solve part B. In part A, we have proved GOF is invertible. That means bijective. Its inverse is exists. Implies this GOF inverse is exist. GOF inverse is exist, which implies this GOF inverse such that GOF is the function from x to z. GOF inverse is the function from z to capital X, and GOF inverse small z, GOF inverse z is equal to x. For every Z belongs to capital Z and X belongs to capital X. It is the equation 1. Since graph is invertible, its inverse is exist. Graph inverse Z is equal to X. For every Z belongs to Z and X belongs to capital X. Since G and F are invertible, implies G inverse, so that G inverse is the function from Z to Y, and G inverse Z small z is equal to small y, and F inverse is the function from y to x, and F inverse y is equal to F inverse y is equal to x. G inverse is the function from Z to Y. F inverse is the function. G inverse is the function from Z to Y, and F inverse is the function from Y to X. G inverse is the function from Z to Y, and F inverse is the function from Y to X. By the composition, F inverse composite to G inverse is the function, so that F inverse G is the function from G inverse is the function from Z to Y, F inverse is the function from Y to X. It is same as the definition of a graph. F is a function from X to Y, G is a function from Y to Z, graph is the function from X to Z. G inverse is the function from Z to Y, F inverse is the function from Y to X. So F inverse composite to G inverse is the function from Z to Y, Y to X, Z to X. Just like the definition of a graph. When graph is defined, F such that X to Y, G such that Y to Z, graph is the function defined from X to Z. Similarly, G inverse is the function from Z to Y, F inverse is the function from Y to X. F inverse composite to G inverse is the function from Z to X. Now we have graph inverse Z to X and F inverse composite to G inverse from Z to X. Both have the same domain and the codomain. Therefore, graph inverse so that Z to X and F inverse is the function. F inverse composite to G inverse so that Z to X. Clear? Here graph inverse so that Z to X and F inverse composite to G inverse is also Z to X. Both have the same domain and a codomain. Therefore, graph inverse and F inverse composite to G inverse are well defined. Clear? Since they have same domain and a codomain. Now, F inverse composite to G inverse Y, or which is same as F inverse Y. This notation is same as this notation. G inverse Y, G inverse Z, sorry, G inverse Z. G inverse is the function from Z to Y. G inverse Z is same as F inverse G inverse Z. This is same as this. Clear? Clear? Okay. G inverse Z is equal to Y. G inverse Z is equal to Y, which is same as F inverse G inverse Z is equal to Y. And F inverse Y is same as X. Implies this F inverse composite to G inverse Z is equal to X. It is equation 2. From equation 1 and 2 we have, from 1 and 2 we have F inverse is equal Z is equal to F inverse composite to G inverse Z. Implies this F inverse is equal to F inverse composite to G inverse. Since this equal to this, implies this equal to this. Since they have same domain and same range. Two functions are equal if they have same domain and same range. For every Z belongs to capital Z, this equal to this. They have same domain and same range, so that the functions are equal. Hence proved. Hence proved. Clear? Clear? Okay.